Hello everyone, and thanks for watching Edupedia World videos. We'll take a break from the physics we've been studying for a while, and now we'll go back to the basics of mathematics and we'll study a topic called linear algebra, which is the mathematical backbone of quantum mechanics. So what linear algebra essentially does is generalizes the notion of vectors. So in high school level physics, a vector has been defined as something which has a magnitude and a direction. But now we will generalize the notion of vectors to include many more things, and of course quantities such as velocity, which have a magnitude and direction, will also be part of vectors. But linear algebra generalizes this notion to include a lot of things which traditionally might not be considered vectors. For example, row matrices or column matrices, and we'll eventually even learn that the states of quantum mechanics qualify as vectors according to linear algebra. So we are redefining the word vectors now, and we'll create a whole set of arithmetic rules which will enable us to solve and calculate relations for what now we will start calling vectors. So the first step is to define a vector space. And just to keep an analogy between what we know as vectors earlier, I'll just take a simple example of vectors in three-dimensional space, vectors such as AI plus BJ plus CK, where I, J and K are the unit vectors in the X, Y and Z direction, A, B and C are the components. So this is what we've earlier known to be a vector. Now we'll expand the definition of vectors to include a lot more than this. So a vector space is basically a set of what is called vectors together with scalars. So a vector space includes vectors plus scalars. In this case, A, B and C would be the scalars and this whole thing would be a vector. And it has to have two operations, addition and scalar multiplication. So what we'll do is we'll redefine vectors, we'll redefine two operations, addition and scalar multiplication, and I'll write down a bunch of rules, and any number of objects which can be divided into vectors and scalars which qualify this rule will be called a vector space, and the objects themselves will be called vectors and scalars. So the rules should be, first let's look at addition. So in terms of addition, and also earlier we've referred to vectors as I hat with a hat over them if they're a unit vector, or let's say L arrow with an arrow of them if they are not a unit vector. But now we'll change that. Now we'll use what is called the bracket formation, which is we'll represent a vector like this, right? Because we are deviating from the original notion, this arrow comes from magnitude and direction definition of vectors, but now we've changed the definition to something abstract. So this is how we'll represent vectors. Now vector addition has to have some rules. The first is alpha vector plus beta is equal to gamma, which means addition has to be closed, meaning if you add two vectors, the result would have to be a third vector. This is clearly true for the original definition of vectors, AI plus BJ plus CK, because if you add two separate vectors, you will get a third vector. Also, vector addition should be commutative. So alpha plus beta should be equal to beta plus alpha. Now these rules you'll find to be quite simple, and they are valid quite logically for the original set of vectors, but what we are doing now is expanding the definition of vectors to say that any set of things called vectors and things called scalars which obey these rules will be called vectors and scalars, and the set of all these together will be called the vector space. So the first rule is the sum of two vectors has to be a third vector. The second rule is vector addition should be associative. It should be commutative. A plus B is equal to B plus A, or alpha plus beta is equal to beta plus alpha. The third rule is it has to be associative as well. So alpha plus beta plus gamma should be equal to alpha plus beta plus gamma. So this is again a simple rule of addition which is generally true for vectors. There are two more rules when it comes to addition. One is that there should exist a zero vector. In our normal definition of vectors, a zero vector would simply be 0i plus 0j plus 0k, and a zero vector should be a vector such that for every other vector, alpha plus 0. Now the zero vector is represented by 0 in a bracket, and this should be equal to the vector alpha. So there should exist a zero vector such that this is true for every vector alpha. And there's finally another rule, which is the existence of the inverse vector. Which means that for every vector alpha, there should exist a vector minus alpha whose sum would give you the zero vector. Now these are quite simple rules, and these rules are valid for obviously normal vectors. If you have ai plus bj plus ck, then the inverse vector would be minus ai minus bj minus ck, and if you add them, you get the zero vector. You add the zero vector to any vector alpha, you get the vector alpha. So these are common sense rules which we've had originally for vectors like these. Now we are saying any set of things which obey rules like this will form our new definition of vectors. So these are the rules for the operation addition. Now let's look at the rules for the operation of scalar multiplication, which means the multiplication of vectors by scalars. Yeah. So for scalar multiplication, the first rule again is it being closed. So any vector alpha multiplied by a scalar a should give you a vector beta. Meaning, if you multiply a vector by a scalar, you get another vector. You don't go outside the vector space in a manner of speaking. And here we know that if ai plus bj plus ck is multiplied by, let's say, 6 or 3 or a number, then we would get another vector. The second rule is that scalar multiplication also has to be distributive, which means a times alpha plus beta should be equal to a times alpha plus a times beta. So you can open the brackets. The third rule is it should be distributive with respect to the scalar multiplication as well. This was just distributive with respect to the vector addition. The third rule is a plus b times alpha. Now remember, everything which is not in these brackets is a scalar. This should be equal to a times alpha plus b times alpha. And as I'm writing down these rules, you can see that these simple rules are obviously valid for vectors of the original definition. Another rule is it is associated with respect to scalar multiplication, which means a times the vector b times alpha is equal to ab times the vector alpha. And finally, there exists zero vector and the unitary vector or the unit vector, which are vectors such that 0 times alpha is equal to the 0 vector and 1 times alpha is equal to alpha. So I wrote down 5 rules for addition of two vectors, then I wrote down these 5 rules for multiplication of scalars, and if we have a set of objects, vectors, and another set of objects, scalars, which obey these rules in terms of vector addition and scalar multiplication, that is what we call a vector space. Now in this case, we've expanded the definition of vectors because now we do not only talk about things which have a magnitude and direction, but things such as row matrix. If you have something like 2, 5, 7, 9, it is a row matrix, and if you look closely, this also satisfies such rules. If you multiply this by a scalar, let's say 5, you get another row matrix. You can multiply a scalar with the sum of two row matrices and you can follow this rule. So row matrices are another thing which follow under this new definition of vectors. And later we will see that the thing which we've been talking about till these videos, which was the wave function or the state of an object in quantum mechanics, that is also another type of vector, and that falls under the category of vector spaces. There are a few other rules which need to be followed and a few other definitions before we can qualify something as a vector space. So let's look at them. A linear combination of vectors of vectors, say alpha, beta, gamma, is another vector of the form of A alpha plus B beta plus C gamma. So this is a linear combination of the vectors alpha, beta and gamma, and let's say this is a vector lambda. Then lambda is said to be linearly dependent on alpha, beta and gamma, which means lambda can be written in terms of alpha, beta and gamma. As an example, if you take the vector 2i plus 3j, it is a linear combination of the vectors I and j. If you multiply I with 2 and j with 3 and add them together, you'll get the vector 2i plus 3j. A vector lambda is said to be linearly independent of the vectors alpha, beta and gamma if it cannot be represented as a linear combination of alpha, beta and gamma. For example, if you take the vectors I and j, then the vector 3k cap is linearly independent of these two vectors, because you can never represent 3k cap as a linear combination of the two vectors I and j, because it is linearly independent. So linearly independent vectors cannot be expressed as a linear combination of the other vectors. And a set of vectors is said to span the space, vector space, if every other vector can be written as a linear combination of them. For example, the vectors I, j and k will be vectors which form a linearly independent set, because this collection spans the vector space. Every single vector in three-dimensional space can be written as a linear combination of I, j and k. For example, 2i plus 3j plus 4k, which is a linear combination. A set of linearly independent vectors, and these are linearly independent themselves, because one cannot be represented as a linear combination of the other. A set of linearly independent vectors are said to form a basis. And for a vector space, the basis is the most important thing. The basis is a set of linearly independent vectors that span the base, meaning every other vector can be written as a linear combination of these vectors. So for example, in three-dimensional space, I, j and k would form a basis, because every other vector can be written as a linear combination of these three. If you have 6-dimensional vector space, then you will need 6 bases. For example, if you have the vector space of column vectors with 1, 2, 3, 4, 5 and 6 terms, so 1, 0, 0, 0, 0, 0, the other would be 0, 1, 0, 0, 0, 0, and so on. There would be 6 vectors like this, 6 column matrices, and obviously you can represent any column matrix as a linear combination of these 6 matrices. So for example, 2, 1, 3, 5, 6, 7 would be 2 times this vector plus 1 times this vector plus 3 times the next vector, and so on. So for every vector space, the basis will be the most important thing, and the number of vectors in that basis is called the dimension. So for 3-dimensional vector space, we have 3 bases. This would be a 6-dimensional vector space because we have 6 elements in the column matrix, and we need 6 separate vectors to form the basis, so that every other vector can be written as a linear combination. Now once we found a basis, our working of vector spaces becomes quite easier, because then every single vector can be represented in terms of that basis. So generally for an n-dimensional vector space, the bases are written as follows: E1, E2 till En. So for 3-dimensional, the first one would be I, the second one would be J, the third one would be K. For n-dimensional matrix, you would have n in different basis vectors. And the good thing about basis vectors is, once you have that, every single vector alpha can be written as a linear combination of these basis vectors. So it can be written as, say, A1, E1, where A1 is a scalar, plus A2, E2, plus A3, E3, so on, plus AN, En. So every single vector alpha can be written like this, which means once you have a basis, a vector alpha has a one-to-one correspondence with a set of scalars A1, A2, A3, An. So a vector alpha can be represented as an n tuple of scalars, n scalars, once you have formed the basis. That is the key. The first step will be to form a basis. And the basis doesn't need to be unique. For example, you can have I, j and k, or you can have the basis being 2i plus 3j, I minus j, and k. Because every vector in two-dimensional space can be written as a linear combination of these two vectors as well. So depending on the basis, you would have the n tuple of scalars, but once you have the basis, this n tuple of scalars is equivalent to this vector alpha. And once you have that, you can also see what the familiar operations will be in terms of that. For example, if you wanted to add two vectors alpha and beta, where alpha is a1 e1 plus a2 e2, and similarly beta has an n tuple of scalars b1 b2 dot 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 till bn. That would be b1 e1 plus b2 e2 plus b3 e3. When you add them, you would get a1 plus b1 times e1, a2 plus b2 times e2, and so on. So this can be represented as a1 plus b1 times a2 plus b2 an plus bn. And this is something we already know. When you have vectors I plus j plus k and 2i minus j plus 3k, and you add them, you just add the three components of the I, j and k vectors, and that gives you the new vector. Similarly, scalar multiplication c times alpha can be written in terms of the n tuple as c a1 c a2 dot 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 c an. The vector 0 vector can be represented as 0, 0, 0, 0, and the vector inverse vector minus alpha will be represented by minus a1 minus a2 dot 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 minus an. So what we've done now is, once we've defined the basis, we have redefined the vector addition and scalar multiplication operations, so that in terms of doing it with the abstract vectors, we can do these operations in terms of the n tuple of scalars. The only disadvantage here, of course, is that you have to decide the basis beforehand, and if you change the basis, then the n tuple of vectors is also changed. But usually you would be working in a constant set of bases, and the basis would be quite simple. Like I mentioned, in the set of row vectors or row matrices, the basis would be 1 0 0 0 0 0 and so on. Now we move on to the new concept, which is a generalization of the dot product, which is the concept of inner products. And up till now we've seen scalar multiplication, which means the multiplication of a vector by a scalar. Now we'll look at the multiplication of two vectors. We already know what dot product is for a familiar vectors. So let's say you have a vector ai plus bj plus ck, and you have another vector di plus ej plus fk. Then the dot product of these two vectors is a scalar ad plus be plus cf. We would like to generalize this to all sorts of vectors, and this is where inner products come into play. So whenever we have two vectors alpha and beta, the inner product is represented like this. Alpha, beta. This is represented as the inner product, and just like the dot product of two vectors is a scalar, the inner product of two vectors is also a scalar. And we have some rules which are obeyed for the dot product, and we would like to generalize those rules for the inner product, so I'll write them down. The first rule is b beta times alpha should be equal to alpha times beta. Right, a dot b is equal to b dot a. The second rule is alpha dot alpha should be greater than or equal to 0, a dot a, and if alpha dot alpha is equal to 0, it means that alpha is the 0 vector. This is also true for the dot product. If you have a dot a is equal to 0, then a has to be 0. And the third rule is alpha times the vector b times beta plus c times gamma is equal to b times alpha in a product with beta plus C times alpha inner product with gamma. So these three rules are followed for the dot product, and we say that if there is any form of product that follows these rules, we refer to that as the inner product. But there is one small difference between these and dot products, and this is that here you have a star which is a complex conjugate. So what we are doing now is we've generalized the concept of vector spaces with one small difference between this and the original. Earlier A, B and C, the scalars, were always real numbers. But now the scalars can be real as well as complex. They're still scalars, they're not vectors, but B and C can be complex numbers in this case, and this is the rule that is slightly different and is followed. And of course, if you have all the scalars being real numbers, then beta alpha will be equal to alpha beta. So this is indeed true for the general dot products as well. And when you have a vector space which also has an inner product such as this, which obeys these three laws, it is called an inner product space. And we'll do a little bit more generalization from the familiar notion of dot products. We know that A dot A is mod A squared. And we would like to generalize this mod A, which is in the previous definition of vectors was the magnitude of a vector, but in this case it is referred to as the norm of the vector, written with two lines. And the norm of any vector alpha is simply the root of the inner product of alpha with itself. So this mod is a generalization of the earlier magnitude, and there are some other definitions which are also generalizations. A unit vector is one who has a mod is equal to 1. It is also called the normal vector. And two vectors are said to be orthogonal if their inner product is 0. So if alpha beta is equal to 0, this means alpha and beta are orthogonal. Another definition is you have a set of vectors which are said to be orthonormal, and this is important because we would like our bases to be orthonormal. Orthonormal just means that every two vectors in that set is both orthogonal and normal, meaning you have a set of vectors, then alpha I inner product with alpha j has to be delta ij. Which means if you take two vectors, their dot product should be 0, and if you take the dot product of one with itself, it should be 1. Delta ij is the Kronecker delta function. And if you pay a little bit of attention, you'll see that all of these rules which we've generalized are also true for the dot product. Right? If you take I, j and k as the bases, then they are an orthonormal set. I dot I is 1, j dot j is 1, k dot k is 1. I dot j is 0, j dot k is 0, and k dot I is 0. So ijk is an orthonormal set, and whenever we try to find the set of bases, we would always prefer the bases to be orthonormal because they would make all of our calculations much simpler. So the reason they would make calculations much simpler is we would be able to solve in terms of the n tuple. So for example, let's say we have alpha and beta, then the inner product of alpha and beta in terms of the n tuple, alpha is equal to the n tuple a1, a2, an, and beta is the n tuple b1, b2, bn. Then alpha dot beta can be a star, a1 star b1 plus a2 star b2 plus plus an star bn. So we are able to get the inner product directly using just the n tuples. We don't need to go into the actual formalism of this, and this is, like I said, the benefit of using an orthonormal basis. This statement would not be true if the basis wasn't orthonormal. The basis has to be orthonormal, meaning ei inner product with ej has to be delta ij. If that is true, then this formula will be true. Another thing, the inner product of alpha with itself would be a1 star dot a1, a2 star dot a2, which would be mod of a1 squared plus mod of a2 squared plus mod of an squared. Where this a1 is a complex number, so mod a1 squared is a positive real number, it is the magnitude of a1. Yeah, so I'd just like to take a brief recap of everything we've done in this video because we have learned a lot. The first is we generalized the notion of vectors. Before learning this video, for you a vector was something which had a magnitude and direction. Now a vector is basically anything which follows certain rules. So you will have two quantities, vectors and scalars, and you would have their operations, vector addition and scalar multiplication. Now we get to define these operations as long as the rules are valid. We defined 5 rules for vector addition and 5 rules for scalar multiplication. Now let's say you have, instead of the I, J and K three-dimensional space, you have 3D vectors, let's say 1, 6 and 9, which is a column matrix, right? This can be written as 1 times 1, 0, 0 plus 6 times 0, 1, 0 plus 9 times 0, 0, 1. So 1, 0, 0, 0, 1, 0 and 0, 0, 1 would be an orthonormal basis. You can verify that for yourself, and this would be a linear combination. So it's up to us to define the values of vector addition and scalar multiplication. In this case, we said if you add two column matrices, you just need to add the individual components. So that was the rule we defined, and if you look at the 5 rules we said need to be followed for vector additions, they are pretty standard rules and they will be followed for this sort of definition. Similarly, we get to define scalar multiplication so that there were 5 more rules valid for scalar multiplication. Once you have type of quantity which you refer to as vectors, another type of quantity which you refer to as scalars, along with 2 operations, vector addition which follows 5 rules and scalar multiplication which follows 5 rules. When you have this, you have what is called a vector space. And it can be quite general. It doesn't need to be things which have a magnitude and direction. Like I said, it can be column matrices, row matrices. It can even be the state of a function or the wave function, as we've seen in the previous videos. So this is the vector space. And if you add the vector space plus something else called the inner product, which again you need to define for those vectors. Once you do that, you get the inner product space. And then we generalized most of what we know for the three-dimensional vectors based on the definition we knew earlier, and we generalized it to all sorts of things which would obey certain rules. And once we have an orthonormal basis, which is generally the first thing we look for in a vector space, we actually had simplified formulas for all sorts of things, such as the addition, scalar multiplication, inner product, and so on. And we also generalized many quantities which we knew from the previous definition of vectors, such as what a unit vector is, what 2 orthogonal vectors are, what the norm of a vector is, and so on. And the topic for the next videos, we'll delve into a little bit more advanced linear algebra, and we'll learn the basics of the formalism required to learn the mathematics of quantum mechanics. Thank you.